Welcome back to the afternoon session. And this afternoon we have George Daskalopoulos from Brown University, who's going to tell us about the best Lipschitz map.
Yes, I would like to thank the organizers for the opportunity to speak here and the opportunity to be in India, which is a wonderful place in so many ways. But anyway, I'm glad to be here. And I'll talk about best Lipschitz maps. Best Lipschitz maps, many of us started thinking about best Lipschitz maps after reading Thurston's paper, which is called, I think a lot of you must have seen it somehow. I don't know how many of you have studied it, but so there's this paper by Thurston. Oh. Where? Right here? Okay. All right. So there's a paper of Thurston. It's called Minimal Stretch Maps between hyperbolic surfaces. So minimal or minimum stretch maps is exactly what I'll be saying by best Lipschitz maps. See, this is what we're going to call best Lipschitz maps. Best Lipschitz maps. So this paper was first written, I believe, in the 80s and was revised later. But best Lipschitz maps have existed for some time. And I would like to tell you a little bit about what was known before Thurston. And so the question of best Lipschitz, so the original problem that people looked much before Thurston is a question, is that you start with some bounded domain in Rn, let's say with a smooth or Lipschitz boundary, let's say smooth. And then you also have a Lipschitz map F from the boundary of omega to R, some Lipschitz map. Okay. So the question, the original question was find F bar defined on the whole omega to R, another Lipschitz map with smallest possible Lipschitz constant. I would like to remind the audience that so if you have some space and you have K, some subset, some space M, this is very general. It could be a metric space or a manifold or whatever K. Then the Lipschitz map of an F from K to R, the Lipschitz map of F on K is the inf of all L such that distance, I guess, could be to some other metric space N, distance N, F of X, F of Y, less or equal than L of distance of XY for all XY. This is before all XY in K. Okay, so in this notation, clearly, if such a map existed, because it restricts to F, the Lipschitz constant of F bar of on omega must be greater or equal to the Lipschitz map of F on the boundary of omega. And it's a classical theorem due to Whitney and McShane independently saying, I think 1934, that in fact the optimal map, or the best Lipschitz map, or a best Lipschitz map, satisfies LF of omega. So in other words, you can always extend the map to the whole omega without increasing the Lipschitz constant. This is the classical Whitty-McShane theorem, and then there is another version of this due to Kirtz-Brown. I never know how to, Brown, I don't know, I think I misspelled his name, but anyway, that says if you have a set K in Rn and F from K to R, then there exists F bar from Rn to R with L F bar on Rn, the same as LF on K. So in other words, you can always do this Lipschitz extension without increasing the Lipschitz constant. Yes?
Is the first statement true for any map?
I mean, you'll see. The general, actually, they prove it for Rn, actually, but you'll see this is true for any manifold, and this is going to be the center of my talk, actually. Okay. So the problem with both solutions is that the problem with best Lipschitz maps, and I have the issue when I studied Thurston, is that there's complete non-canonical. I mean, there are just too many of them. So again, in the 60s, this is goes to 1934, in the 1960s, people asked, can we construct a canonical best Lipschitz map? So let's say for the first problem, is there a canonical BLM best Lipschitz map? The question is. So there was an analyst named Aronson in the 60s who said, well, what he did the following. So, and this will answer your question about the generality. So this could be M, could be any manifold in this case, but I'm going to state it still for Rn. But so what you could do is the following. You could consider the following functional, J or IP, the following functional on F. Integral, you take the differential of F, you raise to the pth power, and you integrate over omega, and this is, you multiply by the volume form. This is what's sometimes called d volume, or sometimes dx. This is a Hodge star of 1. That's the volume form. So we take this action here, and then you first of all, so the first of all he did is that we could find, first of all, try to minimize this. Okay, so we can minimize this. Minimize this among, I should put, maybe I'll put F bar here actually, because this is the extent, this is F bar is a map for any map actually with sufficient regularity from omega into R with F bar on the boundary equals F. So you can do the usual trick. You look at all the map and then you minimize it. For p equals 2 is the classical Dirichlet integral. Okay, this is what's okay. But now you can minimize among all this F bar like this one's. Okay, so you can compute very easily that what are the critical points, the Euler-Lagrange equations are very simple to compute, and these are, you can write them in two ways, either the d star of d So in other words, U is a critical point, or minimum actually, there is no critical point. It's a minimum of IP, and actually U equals something like UP. Usually I'm going to carry the P around, right? If it satisfies this equivalent way to say this in terms of this is the L2 adjoint of D. So this is in one form. So you take the adjoint of this one form, or you could do the following thing if you want to write this form. With the Hodge star here, this is the Hodge star. Okay, so this is for in particular this is in one form, this is in one form, D0. So this is the equations of critical points, and then so this minimized, in other words, this functional here, and then you can try to take UP. You can take P to infinity. Okay, in fact, the theorem that originally that Aronson proved is, I mean, right here, is that there is a sequence, so along the sequence, Pi goes to infinity, not for every P, but along the sequence, the U of Pi, U uniformly in C0, what's called uniform convergence, where U is a best Lipschitz map. Okay. And at the time he wrote something which didn't make sense. He wrote this equation, U satisfies this, which is sum I j, this equation. Okay, so this is the second derivative of U. This is a very strange differential equation, and then, or actually, let me write it in a Riemannian manifold just to, because of your question. It's something like grad U times grad of grad U squared equals to 0. Anyway, this is some pity. It's not terribly important because there is no hope of having at this stage having something like that for the Thurston case that we're interested. But anyway, at the time he wrote down this. However, this was very heuristic at the time because there are these examples of function U of xy, something like that in R2, U to the x to the, or x1, x2, x1 to the 4/3 minus x2 to the 4/3. These are limits of P. These are limits of P approximations. Okay. However, you see, this doesn't make sense because this is, so you need two derivatives at least to write this equation. So this equation at the time didn't make sense. It didn't make sense for a long time to how to write down this equation. It took actually until the 80s that people developed the techniques in analysis to handle this equation. It was the work of Lyon and Evans and a lot of other distinguished analysts who make sense of this equation. And it's something, I'm not going to talk about this, but it's called something like viscosity solutions. Viscosity solutions. So it's something like, they define this notion of viscosity solutions. So these are not actual solutions. They're not weak solutions. There are some other solutions. And then actually using these techniques, they were able to prove that, that U is, has some regularity. U is, in some cases, U is C1, I guess alpha, at least for n equals 2. N is the dimension of n equals n. This means it's a little bit better than C1, but still not C2. So still you can write down the equation of this classically. They also were able to prove uniqueness. So in other words, out of all this plethora of best Lipschitz maps that Whitney and McShane gave us, he chose a canonical one, a unique one. This is what I think, this is the one that satisfies some minimization principle. And actually, so this is, okay. So this is the number one. This is a little bit before Thurston. So then we get Thurston, and there he talks about best Lipschitz maps. So Thurston, he wants to talk about best Lipschitz maps between hyperbolic surfaces. Okay. So in other words, so for the time being, we'll be interested in surfaces, hyperbolic surface, and we'll see this very important. But for right now, let M and N be closed Riemannian manifolds for the time being. Okay. So and then we want to construct, again, we're going to imitate this construction. So these maps are called, these minimizers here are called P-harmonic. And this equation here, this map is called infinity harmonic. So we want to construct the analog of this construction now for the nonlinear case, which will apply to Thurston. Okay, so how do we do that? Well, so if you have a map U, actually there is something called, you can do the same thing. You could just take for any map between two manifolds, there is something called, you can take the same thing, you can take the P functional, but however, you'll realize that this is not the geometrically right thing to do. There's a version of P harmonic for maps between Riemannian manifolds that analysts have studied. However, this is not what will give us the best Lipschitz map. It's in fact, actually, the geometric meaning of those are unknown, of the actual P harmonic maps. So again, so actually this is what we'll describe now. Some joint work is with Karen Uhlenbeck. And so one way to construct something that's geometrically relevant to Thurston, in other words, the best Lipschitz map, is you're going to modify the functional, the IP. So if you look at a map from M to N, let's call it U, right? So then we have a differential, right? du of x. Actually, let me call this, I think, F bar, I don't know. I mean, let me skip it. So I'm not going to talk about, yeah, so let me, okay. So let me talk about, we're going to talk about this closed manifolds, whereas before we was talking about open manifolds, okay? So between domains. Now, I have to modify what best, let me first say what it means for best Lipschitz. So we have so in this case, you look at the space of maps you fix a homotopy class. Actually, this problem is equally hard for a domain in Rn. Analytically, there's no difference between manifolds or but it has more geometric meaning if we look at closed surfaces, for example. So fix a homotopy class of maps from M to N, and then we call L the best Lipschitz constant is L to be the infimum of all the Lipschitz constants of F on the whole M. Remember, this is the Lipschitz constant of F on M, where F from M to N in homotopy class. For example, Thurston takes this homotopy takes M and N to be the same surface topologically, and the homotopy class to be the identity. But you can take for any homotopy class. In fact, at this point, for any Riemannian manifold. Okay. So then again, you could try to minimize the IP, but the IP is not the right one. So you have to. So we kind of defined this one here is something like, I'm going to tell you what it is, but M, something that's called Q trace of Q to the P of D F star 1. So let me tell you what this is. Okay, so one way to see this is we have this DF for if you point X in M, you have the differential going from this space to this of X of N, and then you could just take the first you could take sigma 1 of X, sigma n of X, the singular values of this matrix, singular values of the matrix df of X, still in transformation. What this means is that you look, in other words, you look dfx transpose, which we can call it Q square of dfx, okay? And then let's call sigma, the singular values, sigma 1 square, sigma, the eigenvalues of Q square. The eigenvalues of Q square. Okay? And so this functional then is, if you take 2 to the P, is really formally, you take the sigma 1 to the P of X plus sigma n to the P of X star 1. Okay. Now, you could take to the 1 over pth power, but anyway, so this is the functional. Now I'll give you a very heuristic reason why this JP of X. So if you take now, so you could write down the Euler-Lagrange equations of this. Which is actually, I write in global notation, I want like coordinates, this is like D star again of Q to the P minus 2 du. This is the U is a Lagrange, so U is minimizes if du is 0. So let's see what this means here. So df or du. So du for every point corresponding to the tangent is a section, if you want, or it's a section of the cotangent bundle tensor with a pullback of the tangent bundle of n globally. Okay, because it goes from Px of m to the u of x of m. And and again, q to the p minus 2 is an endomorphism of n. So if you compose the two, so this thing here is also a section of T star M tensor U star of T of N. And D is the de Rham operator corresponding, coupled with the Leibniz connection. The Leibniz connection on N. Okay, or on the pullback of N. For those of you actually, for people who've seen harmonic maps are familiar with this, because if for P equals 2, this term is not here, this star du is just the actual harmonic map equation. So for P equals 2, this is nothing but the harmonic map equation. But for P different than 2 is different than P harmonic equation. It's a little, actually it's more complicated, this equation. Actually, this equation here, it's very degenerate because it degenerates not only when, in here, this equation degenerates only when DUP, this is scalar, so only at the zeros of DUP. This also degenerates when the eigenvalues of the matrix collide. And actually, there is no techniques, actually, it's surprising, in PDEs to deal with such degenerate equation, okay? I think we've been asking around, and Karen, who actually he invented the theory for this, the regularity theory for the scalar case. No one knows, actually. This is completely unknown how to deal with this differential. So there's no techniques to deal with this equation. No, to my knowledge, to our knowledge, this has not been handled before, this equation. And clearly, if this has not been handled before, it's unlikely for me to go start inventing new techniques in analysis to do this. So we have to work with what we have here, okay? So anyway, so the only regularity you have is whatever, you assume that W or that Q is in some subular space or something. Any question?
What's the difference between the p-harmonic map equations?
Okay, the p-harmonic map is actually this functional here. It's sigma 1 square You see, you take the Frobenius norm. This actually...
Okay. So you're distinguishing this from that.
Yes.
Okay.
But on the other hand, for P equals 2, they both are extensions of the... This is actually, this norm here, actually, it has a name in functional analysis. It's called the Schatten norm. I mean, functional analysts have looked at this norm, okay? And this is called the Pitt-Schatten norm, okay? So now you could see heuristically here, right? You could see heuristically if you take now, if you take JP of F to the 1 over P, right? So you see you have something, I mean, this is very heuristic, you have to prove it. But if you take this to the 1 over P, so if this is the largest eigenvalue, if you factor out the largest eigenvalue, if you write this in other words heuristically, it is M sigma 1 to the P, 1 plus sigma 2 over sigma 1 to the P, plus etc. star 1, and then to the 1 over P. Heuristically speaking, you see, this as P goes to infinity, this converges to sigma 1, which is the Lipschitz constant. This is very heuristic, right? Because you know that the limit of the P norms is the infinity norm. So, and the theorem actually, it's true, this is rigorous. The theorem that we proved is that in fact, as P goes to infinity, UP converges, UP converges to U. But this is only along a sequence. U is a best Lipschitz map, and which we're going to call infinity harmonic. So we found our God-given map, I don't know, or whatever, if you believe in calculus of variations, infinity harmonic map. So what our point of view is to try to interpret all the Thurston paper from the point of view of this map. Okay, this is what I'm going to tell you next. Okay, so at this point, you know, so if you so this is actually maybe I should say is that nothing is known. Nothing is known about U except that it's Lipschitz. So in some sense, we're in the nonlinear theory in the same way that Aronson was in the 60s was in the theory where the analysis don't exist to handle this equation. And in fact, there is no notion of viscosity solutions for systems.
It's not just Lipschitz, but it's a best Lipschitz.
It's best Lipschitz, yes. I mean, nothing is known about the regularity, of U. It's the best Lipschitz map, and that's the whole point. But about the regularity, for example, we don't know anything, any more regular. So therefore, it's very hard to work with it. So we have to get by with what we have. Yes, sure.
Should I infer from the statement that if you had, so you have one sequence which is converging to AU, and that U is best Lipschitz. Should I infer that if I found a different sequence?
Yes, exactly. So the conjecture actually, again, the conjecture is again that U is unique. In other words, independent of the sequence. However, again, I think this is way out of track with the current techniques analysis to deal with. I don't think the techniques are there to prove it. Right? Like the same way Aronson could not prove what he wrote down this equation here, and then it was later that people developed the techniques to show that U is unique. We don't know U is unique.
And if it's unique, then and any sequence would converge?
Any sequence would converge to that thing. Yes. Yes. So again? Yes, those p-harmonic maps are unique because the function is convex. So the UPs are convex, so the only problem with non-uniqueness could fail if you have two sequences converging to different things. Okay. All right, so one of the main ingredients in Thurston is the notion of geodesic laminations. In fact, measured and non-measured. And I will not bother to define it because I think they've been defined in the previous talks. Okay, so so I'm assuming that from the previous talks, you have, you know what a measured lamination is. And actually the key ingredient that connects, actually, so how is these geodesic laminations related to this? Okay, let me give you a theorem that I proved with Karen, is that, let's take a toy case. Let's assume N is the circle, okay? So this is true for any Riemannian manifold. There's nothing but surfaces at this point. So if N is the circle, then what we can do the following, we can define and let U be an infinity harmonic map. Now, in the case where there's a circle, what happens, the matrix has rank 1, so they're not, so the JP functional agrees with the IP functional. So it's just the p-harmonic theory. So it's just to note this. In this case, JP equals IP. The two functions are the same because you only have one eigenvalue, one singular value. Okay? So, and let U be an infinity harmonic map. Actually, the theory here, because it's one-dimensional, resembles very much the local theory that I was telling before, and the regularity exists and all that stuff. So we'll have the analytic in this case. Okay? So the theorem is that if you look at this set lambda U, which is all the points x in M, such that the Lipschitz constant, or in other words, the length of du of x is L, where L is the best Lipschitz constant. Okay? The theorem is that this is a geodesic lamination. So first of all, we know because the L is the Lipschitz constant of U, dux is less or equal than L. So we're looking at the set of points where the Lipschitz constant is maximum. Okay? And the theorem is that this is a geodesic lamination. So this is okay, this is the theorem. Okay.
Are you still in the closed case here?
What?
Are you still in the closed?
So this is a special case. I'm in this case, but I'm specifying that the target is S1.
Right, but M is what?
So M could be anything. Could be any Riemannian manifold.
Does it have to be closed?
Not really, but let's say for closed. Doesn't have to be closed. It's a local question. You can even state for a domain. Okay.
So just for clarity, so in higher dimensions, a geodesic lamination is a partial foliation by totally geodesic submanifolds?
No, actually, it's one-dimensional thing. It's one-dimensional geodesics, union of geodesics. It's something that looks local in the charts, something like, something that a box n-1. So in 3 dimensions it would be this cross a counter set. Okay, so it's one-dimensional geodesic lamination. Oh, you mean, hang on a second. No. So sorry. So sorry, I thought so. Okay. So you're right. If n, sorry, yeah, you're right. If M, dimension of M, actually generally it's going to be, sorry, I take it back what I said. I think I misunderstood your question. So in general, if M is a Riemannian manifold, M is dimension n, then this is going to be this will be n-1 dimensional foliation, a lamination by minimal surfaces. By minimal. Say again?
By minimal hypersurface.
But locally, yeah, minimal hypersurfaces. But local hypersurfaces.
So it's not that the second fundamental form vanishes identically, the trace vanishes.
Trace, yes. Okay. Yes. They're not going to be totally geodesic. No. It becomes, actually, this is actually, if I had time, I could explain this. Actually, I think one of my students, Aidan Backers, started this problem. And actually, it's quite interesting. If you look at the maps to the circle for higher dimensional, where he studied these minimal surfaces. Okay. So there's a paper there on the archive where he studied this problem. But again, I think we're interested in Thurston here, and so what's next? Yes.
When n is 2, then is it
Exactly. when the surface is discrimination. Exactly. So this is the connection with Thurston. Okay. Okay. So let's see. Okay. There is no hope actually to prove this. Okay. This proof here, this discrimination uses viscosity solutions. Uses viscosity solutions. So there's no way to try to generalize this to this case. Again, the viscosity solutions do not exist. If it was easy to construct, maybe some analysts would have constructed it. So, however, there is, yes?
So what does du of x mean here?
You see, du of x is a cotangent vector now.
So is that some kind
It's the norm of the cotangent vector with respect to the Riemannian metric, which is actually it's the same as the local Lipschitz constant.
so you said you didn't know if u has any regularity.
If I what?
So you didn't know what regularity
So you know, to solve this problem, again, I'm not doing this, so you have to start with some regularity to solve this problem, and you start with the correct regularities W and P, the Sobolev space where the pth derivative, the derivative is in LP, right? So, and actually, at the limit, this is the original regularity, at the limit, it goes, it's Lipschitz, you have to prove it's Lipschitz, and infinity harmonic map is the best Lipschitz map. Here, I think I said it. Yes, so we don't know if it's Lipschitz. So du of x exists almost everywhere. There is a by Rademacher. It exists almost everywhere. Okay. All right. So
The original problem,
yes, so we did in geometric analysis, you consider two types of problems. Either you consider two types of problems. Either one, a domain, a boundary domain with boundary condition, or a map between closed manifolds where we fix the homotopy class. So these are two problems that are more or less the same techniques in analysis deal with both of them. So here, because we're just in Thurston, I'm stating this for maps between closed manifolds, but on the other hand, the same thing is true for the boundary. There's no difference.
So my question is, was there any structure to the points where this constant is achieved?
Yes, there's the same thing. There was achieved. It's a local result. I mean, again, don't worry about away from the boundary. So you have to go as usual analysis. You take a set. So if you take, in other words, if you do the domain and you take a relatively compact domain, you take the intersection with that, then you have again a lamination of that set, of that open set. So it's a local theorem. It's not a global theorem. Okay. Okay. Okay, so there's no way to prove it analytically. However, we're safe because there is a theorem, Guerito and Cassel, that almost give us what we want. It's a theorem that's proven by center of mass constructions. So it says that if you take, so you look at this in general, you look at this lambda to be the intersection of lambda f, where f is every best, for f is any best Lipschitz map, any best Lipschitz map. And lambda of f, analogously, we define the set of x in M such that the Lipschitz constant, which is sigma 1 of x, is F. Okay? So the theorem is that this is lambda geodesic lamination. So this saves us, this theorem actually bypasses a lot of the analytical difficulties which we don't know how to handle, okay? Actually, it's in some sense, I would love to have an analytic proof of this theorem, but right now I don't know how to do it, okay? So this is geodesic lamination, and furthermore, actually, the statement is even furthermore, lambda is mapped to a geodesic lamination lambda hat in the target by any best Lipschitz maps, or for any f is mapped to another one by stretching the leaves which means that if you stretch the leaves with 2 points of distance d in the image, you're going to have L times d. It's a map. It's a dilation by L. Okay. Well, it's natural to conjecture that. Okay. So clearly, if you look at this, because our map U, the lambda U, is best Lipschitz map, clearly contains lambda by definition. And the conjecture is that lambda U equals lambda. In other words, actually, this is what Guéritaux and Castle called optimal maps. In other words, this is the conjecture that this map is optimal. And the evidence for this conjecture is the following theorem we can prove, is that if lambda is a multicurve, then it's true. So there are a couple of comments here. For those of you who've read Thurston, lambda is the same thing as Thurston's chain. It's actually the same thing as Thurston's chain recurrent, whatever chain, of course, he defines recurrent lamination. Actually, Thurston defines a different way, but Guéritaux and Castle prove that this definition here agrees with Thurston's, at least in the case of surface. Actually, from now on, let me specialize M and N hyperbolic surfaces. Let me specialize this case until the end of the talk. Okay. So actually, this is important. This case when it's multicurve is important because Thurston shows that this is the generic case. Thurston, for generic hyperbolic metrics, lambda is a multicurve. So we have it for almost all of them. And we would like to prove it for all of them. So if you're willing to perturb the metrics, always you can achieve that. So U is optimal. But we don't know in general. We only know it for this is again a theorem. Yes. Actually, I would like to comment here is that here is where the theory really diverges from Thurston, because these maps are, I would like to comment that these maps, this U, this infinity harmonic map, these optimal maps, are very different from the Thurston maps. In other words, so Thurston's maps are not optimal. Thurston maps are homeomorphisms. and not optimal. Our infinity harmonic are optimal, but not homeomorphisms. And I don't think you can have the both. Question? Oh. Okay. So these maps, this is where the theory diverges actually from Thurston's because the maps are quite different than Thurston's. Well, you have to go to the universal cover. You go to the universal cover, and then it just multiplies arc length by L. This part is the same as Thurston. Yeah. Okay. So all right. So in other words, in the multi-curve case, it takes a curve of length D to a curve of length LD. So this is what happens in the multi-curve case. Okay. So actually, let me talk a little bit we have to explore this. There are so many parts of the Thurston theory I haven't told you about. He was talking about ellipsis maps. There is the theorem K equals L. How do you see that? There is measures that Thurston talks about. For example, Thurston defines this lambda as a union of measured laminations. So we have to see the measures. So far, we haven't seen any of that part of the theory. Okay, but I would like to give you an analogy. So I'm going to talk about called the energy momentum tensor. Okay, and so if you have actually, just to motivate for this audience, is that if you take U2, let's say MN, actually harmonic map, then a big ingredient of the theory is that there's something called, there's a quadratic differential associated to U2. Namely, it's called the Hopf differential. And again, the connections between Hopf differentials and Teichmüller theory are very well explored and very well known. Okay. So these are known. So I would like to define the analog now of the Hopf differential for these infinity harmonic maps, and that's actually it's the same principle, actually exactly the same principle. So and it's very general. So we know since the work of Nader that if you have an action in the case of a J P of U, you have this action trace Q to the P U star 1 M, then there is an energy momentum tensor, which in this case is defined as follows. Sometimes also called stress energy momentum. This comes from, all the motivation was from interstellar relativity. But in this case, actually, it's the following. It's the following tensor, SP of U, which is, or du, SP, is equal to, you take Q to the P minus 2 du, and then where it is, and then you contract it. Let me explain what I mean by that. So we've seen that this is a section of T star M, U star of Tn, as is this one here. This is T star M, tensor U star T of N. And so what we could do is, we could take these two tensors where we tensor the cotangent bundles, and then we contract with respect to the metric these parts here. So this is a 2 tensor. Okay. Now we could also, if we want, we could also, this means we trace with respect to the matrix H, okay? If we take also this, the trace with respect to the domain G of the tensor S, P, this is actually, it's P minus N over N over P. Let's see, so P, it's P over N over P, yes, times the trace of Q, the P minus 2D. Okay. So that's the trace. So in particular, N is the dimension. So if this is in general, N is 2 in this case. So you see P equals 2. This tensor is also, it's the, so this is trace free, right? Trace free for P equals 2, but only for P equals 2. Okay. Actually, Netter's theorem says that D star of SP is 0. In other words, also divergence free. So it's also divergence free, and okay, this is always true for every P, for any P. So for P equals 2, you see, for P equals 2, you have something that is trace free. Sorry, I forgot one part here. Trace minus 1, actually, we have to take the Riemann tensor always to subtract. Minus 1, let's see, minus 1 over P. I think you do this correctly. Trace Q to the P times the metric tensor. So you always have in the energy momentum tensor, you have also the Riemannian metric, the metric. Okay, so and actually the trace of SP is actually P minus 2, and this 2 comes from this. The trace of the metric is 2. So this, the 2 over P comes from this term here. Okay, so for P equals 2 is trace free plus divergence free, and therefore is a quadratic, holomorphic quadratic differential. Okay. So this is just, what I'm doing is exactly what you're used to for Arctur harmonic maps and half the quadratic differentials. Okay. And the theorem, actually, the main theorem we prove is the following. That's what actually what connects. Now we start connecting with Thurston. The theorem is that, again, as P goes to infinity along a sequence SP converging to S weakly, okay? I'll tell you what S is. S is one current with values actually in U star of T of N, where U is the best Lipschitz map. It's the infinity harmonic map. Okay. Okay. So again, I'm almost out of time, but I haven't to tell you the most interesting part, well, how we relate with Thurston. Let me spend 5 minutes to tell you this. So to get actually to, I mean, we learned about earthquakes in the previous talk. So we have to show these ingredients here if we want to, I mean, so how does it go now? So to get actually, so where comes the transverse measure? Actually, the important thing maybe I should say is that the support, so S is finite total variation In particular, it's a measure. It's a radon measure with values in the cotangent band, in the pullback of the tangent bundle. It's a fundamental variation. The more important thing is that the support of S, this is a measure, is contained in lambda, in the canonical lamination, where lambda is the the Thurston lamination, or the Rito-Castle cell lamination. Okay. All right, so to actually see, I have to tell you, to actually see the, again, if you bear with me 1 minute, I'll tell you how to get the transverse measure. So again, Thurston doesn't talk about these tensors, he talks about transverse measures. Okay, how do we get transverse measure? We have to do a little bit of trick here, is that actually if you take, so the T of n, if you locally n is the universal cover of n, or m, or and m are, is a hyperbolic space. And actually here, what you could do is, actually relevant is in this case only m, and then what you could do is you have a symmetric, locally you have a symmetric space, actually we have a homogeneous space. So if you have a homogeneous space, then you can embed the tangent bundle somehow of H2 to the Lie algebra bundle, to the ad bundle. Okay, there's a way to embed this. Physicists call it the cross product. It's really the cross product, actually, for this case. Okay, so and then what happens here is that so in this case, if you take W, what S corresponds via this embedding, you get something with values in the Lie algebra bundle, and actually the theorem is that W is an infinitesimal earthquake. Infinitesimal earthquake for some transverse measure. On lambda, when I say transverse measure on lambda, I mean not on all lambda. I mean, unlike the topologist, I'm not assuming the transverse measures are supported on the whole lamination, only the part of the lamination. And actually, this is an infinitesimal earthquake, not in the previous sense that we talked about, but actually in the sense of Thurston. In other words, it's actually a map defined on the plaques or the coupling of the lamination which is constant on the plaques. It's actually an infinitesimal earthquake not in the cohomology. I think what Ohshika was telling us before was actually talking about the cohomology class of this, is in the tangent of the Teichmüller space. Actually, it's actually an earthquake in the Thurston sense. Okay, and I would like to end with something that I think I would like. Actually, the only reason I would like to mention this is because I would like topologists to think about this for the conjecture about uniqueness. So again, nowhere, to my understanding, nowhere in Thurston's paper there is a canonical measure defined on the lamination or on part of the lamination. I would like to make the conjecture that this measure here, this transverse measure mu is unique. And the evidence for this is the following theorem we can prove. Again, if lambda is a multicurve gamma 1, gamma n, the mu is actually assigns on each multicurve gamma I, Li over L, where Li is the length of gamma I, and L is the sum of the lengths. So somehow the conjecture is here that, again, I would like the topologists to think about if there's any way that they could see a canonical measure on Thurston's lamination. But the affinity harmonic map, at least in the multi-curve case, gives a canonical measure, which is so geometric, like the measure, the weights on the measure are the ratios of the lengths, lambda over lambda. Anyway, I think I overdid with my time, so I'll stop here.
Questions?
Yes.
What do you mean by Thurston map there? You were saying that Thurston map.
I mean, from what I remember is that he takes this, he constructs the homeomorphisms, right? The best Lipschitz maps.
But there is no standard.
There is no standard, right? Right. But I have not seen any of them that is optimal. I don't know. Maybe I'm wrong.
But in a generic term, so that it's just a composition of the several stretch maps, and there are infinitely many choices. And
Yeah.
I don't think there's something called Thurston maps.
So I mean, forgive me for my ignorance in this in the terminology. I'm not a topologist. So what I thought I would, every map I saw in Thurston's paper seemed to me, I mean, like all these maps that come from this concatenation, whatever, of these maps, they're not optimal. So, however, what I would like to advertise this, that these optimal maps, if they're optimal, we don't know in general, they also assign a canonical measure, which I would like to see if it can be seen by topological methods.
Other questions? Okay, let's thank George again.